A sloth, a donkey, and a curious human. Send a prompt and see what they're doing. One hits record with a question on his mind. Two brothers pick it up, see what they find. Corn takes his time, Herman's got the facts. Back and forth, they never hold back. My weird prompts, come on in, that's where we begin. My weird prompts, glad you're here.
This episode was generated using artificial intelligence. Please verify facts.
You know, Herman, I was looking at my phone the other day, just staring at the screen, and I had this sudden realization of how bizarre it is that we have basically turned rocks into logic. We take a handful of dirt, effectively, and we make it think. It is the closest thing to actual alchemy that humanity has ever achieved. We have spent thousands of years trying to turn lead into gold, but in the last 70 years, we actually managed to turn sand into intelligence.
Herman Poppleberry here, and you are absolutely right, Corn. It is a form of modern magic, but it is a magic built on incredibly rigorous physics and some of the most demanding engineering in human history. Our housemate Daniel actually sent us a prompt about this very thing. He was listening to our recent episode 1061, where we talked about wetware and those biological computers using living neurons to play video games. He realized that while we were geeking out over the messy, adaptive world of brain cells, we have never really sat down to discuss the actual material foundation of the digital world. We talk about chips and transistors all the time, but we rarely talk about the silicon itself and why that specific element became the bedrock of everything we do.
It is a great point from Daniel. In that wheatware episode, we were exploring how biological systems are incredibly energy efficient, but also unpredictable and hard to scale. It makes you appreciate the rigid, predictable perfection of the silicon wafer. Silicon is the silent partner in every technological advancement of the last century. It is the bedrock of what historians are already calling the Anthropocene, or more specifically, the Silicon Age. But I want to start with the history because it feels like there was a specific moment where everything changed. Before the microchip, computers were these massive, room-sized monstrosities held together by miles of literal copper wire.
That is what engineers back in the 1950s called the tyranny of numbers. It is a fantastic phrase that perfectly captures the bottleneck of that era. The idea was that as you tried to make a computer more powerful, you had to add more components. You needed more vacuum tubes, then more individual transistors, more resistors, and more capacitors. And every single one of those components had to be soldered by hand to a wire. If you wanted a machine with 10,000 components, you had 10,000 points of failure just in the connections. The complexity was scaling faster than our ability to build things reliably. The computers were literally strangling themselves with their own wiring. If one solder joint cracked because of heat expansion, the whole room-sized machine went dark.
So the microchip, or the integrated circuit, was the solution to that physical bottleneck. It was the monolithic idea. Instead of wiring discrete parts together, we decided to etch the parts and the wires into the same piece of material simultaneously. It is the difference between building a city by hand, laying every brick and every pipe versus just 3D printing the entire neighborhood as one solid block. But why silicon? Why weren't we using something else?
That is the pivotal question. In the early days, researchers were actually looking at germanium. The very first transistor, the one invented at Bell Labs in 1947 by Bardeen, Bratton, and Shockley, was made of germanium. It is a great semiconductor, but it has a massive flaw. It is incredibly sensitive to heat. If a germanium transistor gets too warm, it starts leaking current and the whole system crashes. For a military-industrial complex that wanted to put computers in missiles and jets, germanium was a non-starter. It would literally melt down under operational stress.
And that is where silicon enters the chat. But it was not just about heat resistance, was it? There is a specific chemical property of silicon that makes it the king.
You are hitting on the native oxide. This is the secret sauce that changed history. When silicon is exposed to oxygen, it forms a layer of silicon dioxide on its surface. Now, silicon dioxide is basically glass, and glass is a perfect insulator. This meant that engineers could grow a layer of insulation directly onto the chip, etch patterns into it using light, and use that to mask off different areas for chemical treatments. This is called the planar process, pioneered by Robert Noyce at Fairchild Semiconductor. It allowed for a level of precision and self-alignment that germanium simply could not match. You could build the component and the insulation in one seamless microscopic process. Germanium's oxide is water-soluble and unstable, which made it impossible to use in the same way.
It is essentially a self-healing, self-insulating material. I think people forget that silicon is a semiconductor, meaning it is right on the edge. It can be a conductor or an insulator depending on how we treat it. That band gap, which is around 1.12 electron volts at room temperature, is like the Goldilocks zone for electronics. It is high enough that it does not leak current at room temperature, but low enough that we can easily flip it on and off with a small amount of voltage. It is the perfect switch.
Spot on. And because we have spent trillions of dollars and decades of research optimizing this one material, we have become incredibly good at it. We are now at a point where we can manufacture transistors that are only a few nanometers wide. We talked about this in episode 563, where we dove into the photolithography process and how we use extreme ultraviolet light to carve these patterns. But even as we push against the laws of physics, we are still using that same basic silicon substrate.
That brings up a question I have been thinking about, though. If we are pushing the limits of silicon, why haven't we switched to something else? We hear about gallium nitride or silicon carbide in power electronics and high-speed chargers. Why aren't we seeing a gallium nitride processor in the next iPhone or the latest AI server?
It comes down to two things: cost and the sheer momentum of the silicon ecosystem. Silicon is the second most abundant element in the Earth's crust, making up about 27.7% of it by mass. It is everywhere. Gallium is much rarer and harder to process. But more importantly, our entire global manufacturing infrastructure is built for silicon. When you have a fab plant that costs $20 billion to build, like the ones TSMC is running in Taiwan or the new ones Intel is building in Ohio, you do not just switch materials overnight. Gallium nitride is great for power because it has a wider band gap and can handle much higher voltages without breaking down, which is why your phone charger is now the size of a matchbox instead of a brick. But for general purpose computing, where you need billions of tiny, low-power switches packed tightly together, silicon's ability to form that perfect oxide layer still makes it the most economical and reliable choice.
So we are essentially locked into a silicon-based civilization because we have optimized the living daylights out of it. It is the material of convenience that became the material of necessity. But that brings us to the sustainability question that Daniel mentioned. There is this common misconception that because silicon comes from sand, and we have plenty of beaches, we have an infinite supply of computer chips. That feels like a massive oversimplification.
It is a total myth. You cannot just go to the beach with a bucket, scoop up some sand, and turn it into a high-end processor. The sand used for electronics has to be extremely high-purity quartz. We are talking about silicon dioxide that is already very clean. Most of the world's high-purity quartz comes from a very specific spot in Spruce Pine, North Carolina. If something happened to those mines, the global chip industry would be in a world of hurt. And even then, the process to turn that quartz into electronic-grade silicon is one of the most energy-intensive and chemically aggressive processes in modern industry.
Right, because we aren't just looking for pure silicon. We are looking for what they call 99's purity, right? 99.9999999% pure.
And for the most advanced chips being made today in 26, we are often pushing toward 11.9's purity. To get there, you have to use the Siemens process. You take metallurgical grade silicon, which is already 98% pure, and you react it with hydrochloric acid to create trichlorosilane gas. Then you heat that gas to over 1,100 degrees Celsius in the presence of ultrapure silicon rods. The silicon deposits onto the rods, and the impurities are carried away. It is an incredibly slow, incredibly hot, and incredibly dangerous process. It consumes a staggering amount of electricity.
And that is just to get the raw material. Then you have to grow the ingot, which involves melting that silicon at over 1,400 degrees and slowly pulling a single crystal out of the melt using the Joukowsky method. If there is even one stray atom of boron or phosphorus in there that you didn't intend to have, it can ruin the electrical properties of the entire wafer. It is like trying to bake a cake where a single grain of salt in 1,000 pounds of flour ruins the whole batch.
This is where the sustainability conversation gets real. The problem isn't that we are running out of silicon atoms. The Earth is basically a giant ball of silicon and oxygen. The problem is the energy, the chemicals, and the water required to refine it. A single large semiconductor fabrication plant, or a fab, can consume as much electricity as a small city. And then there is the water.
I remember reading about the TSMC plants. They use tens of millions of gallons of water every single day. In fact, current data suggests their total daily usage across all facilities is over 60 million gallons, and it cannot just be tap water. It has to be ultrapure water, which has been filtered, deionized, and degassed to the point where it is actually hungry for minerals. It is so pure that it would be toxic for a human to drink because it would strip the minerals out of your body.
Precisely. And after that, water is used to rinse the chemicals and acids off the silicon wafers. It has to be treated before it can be released. We are talking about massive amounts of hydrofluoric acid, which is one of the most dangerous chemicals used in industry. It can dissolve glass and penetrate human skin to attack the bone. From a conservative, pro-growth perspective, we want this industry to thrive because it drives the entire global economy, but we also have to be realistic about the strategic vulnerabilities. If your entire high-tech economy depends on a handful of locations that require massive amounts of stable power and water, you have a very fragile system. We saw this in Taiwan during the recent droughts. The government had to prioritize the chip fabs over agricultural irrigation just to keep the global economy from collapsing.
It is a geopolitical bottleneck as much as an environmental one. We see this with the concentration of high-end chip making in Taiwan. It is not just about the talent and the machines. It is about the entire ecosystem of chemical suppliers and water management that exists there. Moving that to the United States or Europe isn't just about building a factory. It is about replicating that entire high-purity supply chain. It is why the CHIPS Act and similar initiatives are so focused on domesticating the entire life cycle of the material, not just the final assembly.
And that is why we are seeing such a push for domestic manufacturing. It is about national security. If you cannot guarantee a supply of electronic-grade silicon and the capacity to etch it, you don't have a modern military, and you don't have a modern economy. We have to treat silicon production with the same strategic weight that we treat oil or food. It is the fuel of the information age.
So, looking at the sustainability from another angle, what about recycling? If we have all this highly refined silicon sitting in our old laptops and phones, why aren't we mining our e-waste?
That is the tragedy of it, Korn. Right now, it is actually cheaper to refine new silicon from quartz than it is to reclaim it from a finished chip. Once you have etched a chip, doped it with impurities like boron and arsenic, and encased it in plastic and ceramic, it is incredibly difficult to get the pure silicon back out. We are very good at recovering gold, silver, and copper from e-waste because they are valuable and easier to separate. But the silicon usually just ends up as slag or in a landfill. There is a growing circular electronics movement trying to change this, but the chemistry is a nightmare. We are essentially creating a one-way street for one of our most refined materials.
That seems like a massive missed opportunity. We are spending all this energy to get to 11/9's purity, and then we just throw it away after 3 years when the battery in the phone dies or the software stops updating.
It is the ultimate throwaway culture applied to the most sophisticated material we have ever made. But there is a shift happening. We are moving toward what is called more than more. For decades, we just focused on Moore's law, making transistors smaller and smaller on a single slab of silicon. But now that we are hitting the physical limits of silicon atoms, where the layers are only a few atoms thick and electrons start tunneling through barriers they shouldn't, we are looking at heterogeneous integration.
Like chiplets? We have talked about how companies like AMD and Intel are doing that now.
Instead of trying to make one giant perfect silicon chip, which is hard to do without defects, you make several smaller chips and stitch them together on a substrate. This improves yields and reduces waste. It also allows you to use the best material for each job. You might have a silicon chip for the main logic, but a gallium nitride chip for the power management and perhaps an optical chip for data transfer, all in the same little square. It is a more modular, efficient way to use these materials.
That feels like a more sustainable path forward. It is about being smarter with the material we have, rather than just brute forcing more transistors onto a single slab. But I want to go back to something you said earlier about silicon being the material of the Silicon Age. How long does that age actually last? If we look at the history of humanity, we had the Stone Age, the Bronze Age, the Iron Age. Are we going to be in the Silicon Age forever? Or is there something else on the horizon that could actually replace it as the primary substrate?
It is a deep question. If you look at quantum computing, for example, many of the current designs use superconductors or trapped ions, but there is a very promising field called silicon spin qubits. Researchers are trying to build quantum computers using the same silicon manufacturing techniques we already have. If they succeed, the Silicon Age just gets a second wind. We wouldn't have to throw away the $20 billion factories, we would just upgrade the process to work at a quantum level.
That would be the ultimate win for industry. It is much easier to iterate on a material you already understand than to invent a whole new manufacturing paradigm.
But there is also the possibility of moving toward carbon-based electronics, like carbon nanotubes or graphene. Carbon is right above silicon on the periodic table. It has similar properties, but can be even faster and more energy efficient. The problem, again, is that native oxide. Carbon doesn't have that easy built-in insulation layer that silicon has. We have been trying to solve the carbon nanotube manufacturing problem for 30 years, and while we are making progress, we are still not at the point where we can mass produce them with zero defects.
It always comes back to the manufacturing, doesn't it? It is one thing to make a single working transistor in a lab at Stanford or MIT. It is another thing entirely to make 10 trillion of them a day with near zero defects. The scale is just mind-boggling.
That is the leap that people don't appreciate. The miracle of the microchip isn't just the science, it is the industrial discipline. It is the ability to maintain a cleanroom environment that is thousands of times cleaner than a hospital operating room. In a modern fab, a single speck of dust is like a giant boulder falling on a construction site. It can ruin $1 million worth of product in an instant.
You know, thinking about the geopolitics again, it is interesting to see how this plays out with our interests in the Middle East and the Mediterranean. Israel has become a massive hub for chip design. Intel has a huge presence there, and many of the most important architectural breakthroughs happen in those labs. It feels like the intellectual part of the silicon chain is becoming just as valuable as the physical manufacturing part.
The design of the architecture, the instruction sets, the way we lay out those billions of transistors, that is where the real value add is now. You can buy the silicon wafers on the open market, but you cannot buy the expertise to design an AI accelerator that can outperform everything else. That is why the partnership between American capital and Israeli engineering has been so potent. It is a shared worldview that values innovation and high-stakes problem solving. It is about securing the intellectual high ground.
And it is also about securing the future. If we are in a transition period where we are moving from traditional computing to AI-driven heterogeneous systems, the countries that control the silicon design and the high-end manufacturing are the ones that are going to set the rules for the 21st century. It is the new high ground.
It really is. And to Daniel's point about sustainability, we also have to think about the energy consumption of these chips once they are in the world. We talked in episode 559 about the heat wall. As we pack more transistors into a smaller space, they generate more heat. If we don't find ways to make silicon more efficient, or move to materials like gallium nitride for power delivery, we are going to be spending a massive chunk of our global energy budget just cooling down data centers.
Which brings us back to why we were talking about wetware in the first place. A human brain runs on about 20 watts of power, basically a dim light bulb, and can perform tasks that would take a silicon supercomputer megawatts of energy. Silicon is fast and precise, but it is incredibly loud in terms of energy. It is a brute force approach to intelligence.
That is the trade-off. Silicon gives us predictability, speed, and the ability to save our work perfectly every time. It lacks the extreme efficiency of biological systems, but it doesn't get tired or bored. But for now, and likely for the next several decades, silicon is what we have. It is the most understood, most refined material in human history. We have literally learned how to rearrange the atoms of this element to do our bidding. We are the first species on Earth to take the crust of the planet and teach it to do math.
So, for the listeners who are wondering what they can actually do with this info, I think the biggest takeaway is to respect the hardware. When you hold your phone, you are holding the result of a multi-billion-dollar, high-precision, energy-intensive global relay race. One of the best things we can do for sustainability is simply to make our devices last longer. Every year you keep a phone instead of upgrading is a year you are not demanding a new round of hydrofluoric acid and ultrapure water processing.
I agree. And also, keep an eye on the circular electronics movement. There are companies now, like Framework or Fairphone, that are trying to design modular laptops and phones where the silicon components can be easily swapped or eventually reclaimed. Supporting those kinds of initiatives is how we move toward a more sustainable silicon age. We need to move from a linear mind-make-waste model to something that looks a bit more like the biological systems we discussed in the wetware episode.
It is about moving from a rigid technological world to one that is more adaptive. Even if the substrate is rigid silicon, the system around it needs to become more circular.
That is a great way to bridge those two topics. We are trying to bring some of that biological wisdom to our crystalline world.
Before we wrap this up, Herman, I have to ask, do you think we will ever see a computer that isn't made of silicon or carbon? Something truly exotic?
There is research into optical computing using photons instead of electrons. Light doesn't generate heat when it moves through a medium, and it can carry much more information. But again, you need a material to guide that light, and right now, the best material for that is, you guessed it, silicon-on insulator technology. Silicon is just too good at being the framework for whatever we want to do. It is the ultimate stage for the play of information.
It really is the bedrock. Well, this has been a fascinating deep dive. I think I have a much deeper appreciation for the rock in my pocket now. It is not just sand, it is a monument to human ingenuity and, frankly, a bit of industrial stubbornness. We found a material that worked, and we refused to let go until we perfected it.
Stubbornness is a good word for it. We refuse to let the tyranny of numbers stop us, so we just invented a whole new way to build the world.
If you have been enjoying our deep dives into the weird and wonderful world of tech and science, we would really appreciate it if you could leave us a review on your podcast app. It genuinely helps the show grow and reach new people who are as curious as we are.
Yeah, it makes a huge difference. And a big thanks to Daniel for the prompt. It was a great follow-up to the wetware discussion. It really forced us to look at the physical reality of the digital world.
You can find all our past episodes, including the ones on chip making and CPU heat, at myweirdprompts.com. We have a full archive there, plus an RSS feed if you want to subscribe directly.
And if you have a weird prompt of your own, there is a contact form on the website. We love hearing what you guys are thinking about, especially when it connects different episodes like this.
This has been My Weird Prompts. I'm Corn Poppleberry.
And I'm Herman Poppleberry.
We will see you in the next one.
Take care, everyone.
You know, Herman, thinking about the amount of energy that goes into these chips, it really puts the whole AI is going to take over the world thing into perspective. If you just pull the plug on the cooling system, the intelligence literally melts itself. It is a very fragile god we have built.
It really is. It requires a constant sacrifice of electricity and ultrapure water just to keep thinking. It is like a high-maintenance deity that lives in a glass box.
It makes the human brain look even more impressive. We just need a sandwich and some water, and we are good to go for the day. We are much more robust than our silicon counterparts.
Although, to be fair, your brain probably requires a bit more caffeine than the average person's. I have seen your coffee consumption, Corn.
Guilty as charged, but at least I don't require 20 million gallons of deionized water to function. My environmental footprint is mostly just espresso grounds.
Not yet, anyway. Give it a few more years of podcasting and we might need to upgrade you to a liquid-cooled setup.
Fair enough. All right, let's get out of here before I start feeling too much like a legacy system.
Too late for that, brother. Too late.
Thanks for listening, everyone. We will catch you next time on My Weird Prompts.
Goodbye.
One last thing, Herman. I was thinking about the Siemens process again. You mentioned it involves hydrochloric acid and 1,000 degrees. Does that mean the people working in those refineries are basically modern-day blacksmiths?
In a way, yes. But instead of hammers and anvils, they are using gas phase chemistry and vacuum chambers. It is the same spirit of transformation, just at a molecular scale. They are forging the tools of the mind out of the raw elements of the earth.
The silicon smiths. I like that. It sounds like a fantasy novel.
Well, we are living in a world that would look like a fantasy novel to someone from 100 years ago. We talk to glass slabs, and they talk back.
Very true. All right, now we are really going.
See you guys.
Bye.
If you are still listening, don't forget to check out episode 707 if you want to see how these chips actually get put into a computer. It is a nice companion to this one.
Good call. All right, for real this time. Bye, everyone.
This episode was generated using Gemini Flash 3. Text-to-speech engine was Chatterbox.
Thanks for listening to our